Okay. So let us start. You see my screen? I rearranged it so the latest is now at the top. That's more convenient. And here are the news. And I rearranged it again. I think we will start from theory and from news, and then we'll switch to some exercises. Because guys, when we started doing exercises, that was so exciting that everybody said, yeah, exercises are it. But then exercises were not, I believe, like what you expected them to be. And the excitement died out, and maybe the theory is more exciting. And besides, we have some very interesting theory from just yesterday. So let's go there. Let's look. So that is the announcement. I will show you this announcement in a second, but I want to tell you that that announcement came to me by way of my wife. She is watching all the news. She likes reading New York Times, and some journalist was writing about this. It was an amazing story because I have to tell her that I don't like journalist style, and of course she gives me a hard time because of that. But in any case, starting from New York Times, then you go to this. So let's open, and that's already more close to the source. That's Fermilab. Okay, so guys, none of us is in Chicago right now, but that is in Chicago. Fermi Labs it's an amazing architectural thing. So let's find them. Labs. Yeah, right here. Give me the picture. Quite an amazing thing they built there, right? You see this? That's the building that they have built. And we also saw their famous, well, how would you call it? Collider. I understood finally what it does. It takes the particles and speeds them up almost to the speed of light, and that's why it's round. So it's running in a circle. I think that Greek, they considered it to be not humane to be running in the circle. They never did. They never had the races like we do in the circle. Instead, they would run from one city to another. And it's up to you to handle the logistics. Okay, back to where we were. That was the announcement that they made. And the announcement is about Muon. Now, to me, honestly, that was all completely new. But now I'm comfortable with you, so I can pretend as if I know what I am talking about. Muon is another particle. Muon is a relative of electron, I believe, but it is 100 times bigger and heavier. It's an interesting particle because this muon only lives 1/1000th of a second. I mean, that's all crazy, but how did they find it? It's up to them. But it is created and then it disappears. Nevertheless, they were able to create a whole array of those muons. And that's the beginning of the story. That's still ancient times, because then they started measuring a certain factor of this Newton. I think it is a spin, and they measured it, and it should be, well, there should be the number 2. That's why it's G minus 2. Should be exactly 2. But the fact that it's not exactly 2, it's close. It's, I wonder if they show us a number. Yeah, that's the number. That's the new measurement. It's almost 2, not quite 2. And if you subtract 2 from this G, then you get 0.0002. Well, that changes the world. As they explain, because it's not exactly 0 here, that is our window into another world. You would be surprised how can one little portion of a unit give you a window into another world, but just keep staying with me. Hi, Ken, by the way, I see you came and I want to allow you to talk. Yeah, and I'm talking about the muon they newly discovered not the particle they knew about, that it opens a window into yet another world. That is the new thing that was announced, I believe, yeah, well, 10th, and what's today, 11th? Yeah, that's the announcement as of yesterday. So this muon should have the spin of 2, and it has 0.002. Well, that's a little window into the other world. How precise are they? Maybe it's just an error of measurement. No, they say that's our error of measurement. And we are quite certain that this is too. So I think there was another physical discovery, which all was just because it doesn't quite, yeah, that's the Bell constant. It should be 2, and instead of 2.8, and that makes all the difference. And all of the nuclear physics depends upon this. So another case like this, what then? So far it's numbers. Well, practically they say that there must be a lot of particles that are here that we don't know about. Now, keep being amazed, because I'm very much amazed. What they talk about is that here is a current theory of the world right here. That's the current theory of the world, which has particles. I thought that was a beautiful picture, and Department of Energy explains this to us. And it has those particles. Let's look at them. Like I don't even know, electron. Okay, that's the only one I know, and neutrino, right? But then in the middle, there is the Higgs boson. That's another particle, which they call a God particle. But I think they found something else, and they all agreed that they found something else. So amazing as this picture is, it's all news. The modern news is this muon. And the fact is that there is no empty space. When you have what you would normally call an empty space, it is full of particles that are being created and they disappear. All right, well, I think that's enough. So in other words, this muon shows you a window into a whole new world of particles that is created and disappeared all the time. And that world is governed by yet another force. So I don't know where it was, but classically there are 4 forces. There's gravity, there's electromagnetism, and there are a couple of different forces in the atoms. Well, this is force number 5. All right, so amazing miracle things, but I have some nice slides about this. I think I have them here. Muon. Okay, so I'll put it in this slide view. Okay, that's that same big thing that everybody's amazed about. By the way, I just found out I'm reading the book about Oppenheimer, and Oppenheimer is connected to Lorentz. And Lorentz is an interesting figure who invented the whole idea. He invented the idea of taking a very big magnet and having particles run around in a circle until it goes and crashes into another particle. So it was not an ancient thing. They just invented it in the 40s, 50s. Okay, that's what it looks like. Now, that is what it says. Let's read, because I think it's an amazing to see such statements in Fermi Labs press release. Those scientists do press releases, and they say muon, a short-lived particle, right here, short-lived particle, and they have a strong magnetic field in an empty space. Just as I was telling you, there is an empty space of vacuum, which is not really vacuum. It's not never empty. It is instead full of virtual particles that is popping in and out of existence. Now, tell me if it's crazy, right? If you think it's crazy, I'll put it in the chat. Plus one, right? Do this. Yeah? That it is crazy. Okay. Now that's not all. That's a little bit more of the explanation, and that's scientists talking. That's not the journalist. It says if you take this constant and subtract 2 and pronounce it G minus 2, then you're in the know. But the fact that it is not 0 shows you that there are particles that blink in and out of existence. And so it's in addition to the standard model, which I showed you, and I see there's a chat. What's in the chat? You did. Aisha, you did +2. Thank you. All right. +1, you did. Dense particles. Okay, that's it. That's here. I told you this great news, and I thought that was amazing, and it came just in time for our webinar. Okay, that's the latest news. I also found out more about Intel Initiative. Intel Initiative, it's the slides. If you click on this link, it's here. So here is Intel. It turns out that IBM is not the only player in the quantum computing. How can there be another player? That seems that IBM is really big and doing great things. Well, Intel's idea is somewhat different. IBM gives you quantum computing online, so you can create an account and then you'll be submitting your jobs for quantum computing. Now, uh, um, you don't necessarily submit it to quantum computer. You can do emulation. And I will later on, not today, but later on, I will tell you that there's a new library in Qiskit in quantum computing, where it's kind of more production-like, so called runtime, Qiskit runtime. And that's pretty big. How can you compete with it? Intel has a different idea. They make small computers. They're not as grand as 433 qubits of IBM, and they are not shooting for thousands, but their goal is educating the public and also giving them like a little quantum calculator. So let's look at this. Well, it's not that little, it's 40, I think, or something like that, qubits, but this you can buy. Well, me and you probably will not buy it, but quite a few universities already bought it. That's Intel's idea, and they then ask 5 universities to create courses about this, and these universities, having created the courses, will give them to other universities, and that's the idea. That you see Intel's full stack approach to quantum computing. That includes, first of all, yes, they do have the hardware, but in addition to the hardware, they also created their own C++ emulator. I guess they chose it because it's faster, or just to be different. If you are Python, like just like IBM, what's the big deal? So they have quantum runtime, and that's the idea, promote the whole education. We remember that now we're focusing on get ready for the future today. And that also is their idea. In fact, they subscribe to this uh, Los Alamos National Lab idea that there will be a need for a great many programmers. I'll tell you what I'll do without it, with it. But great many programmers are not needed today, not yet, but they're preparing for that. So that's their approach. They have the SDK, software development kit, which you can get into info. Like I did subscribe to all of these, and I'm trying to get access to that. So I'll show you more once I'm in there, and that's the potential applications. Now, these will not surprise you, and if these applications become real, they will probably happen on IBM. But that has to be here to explain what we're talking about, and a nice quantum computer as it usually is, except that there is a little influence side. That's what you see, and that I don't know what the picture is. Okay, let me pause. Let me pause, and in fact, let me stop share, because that gives you a chance to ask a question. So if you have any questions, that maybe prompts you to ask a question. But if you have no questions, what I will do is share the screen again. And I think I have the next lab for you, and I will have quite a few labs in the coming weeks. And coming weeks will end on August 25. In other words, that's exactly Friday. Let's, sorry to bother you about this, but let's look on my calendar. And see how does that agree with my webinar. So here we are. That's my calendar. Calendar. Okay. August 25. Okay. Oh, guys. So on that day, 2 weeks from now, I will be taking the Qiskit test. That is, I'm already signed up, so I'll have to do it. And at our webinar, I will announce what's the result. It's either pass or it's lose. I usually don't pass. It takes me a long time to pass any certification. The last one was Google certification. I got it in the end. It was very hard. I was surprised I got it. And I got a car license plate sticker. All right. So yes, everything is normal, but I will take the test. So I'll be doing mostly that, and I will have labs for you. And as I promised, there will be less for you, and there will be one lab for you now. All right. So what I will do is this. Let's go to this lab. And first, let's look at what we want to do. So I'll give you that link. I'll give you that link on the chat. And that's something practical that you can do here. Okay. So if I click on that link that I just gave you, it opens. And I think I'll do well if I will first explain you, but then I'll try to run it with you, and I will try to run it in the free Colab environment so that you'll get the chance to practically do this. Okay, so we're back to square zero, at least square one. We're going to create a little circuit, little quantum computers, and run them. But we'll start very low. We're not doing dozens or thousands or millions of qubits. We will do this. We will create a circuit, and we will also take an emulator, something that you can run here without bothering IBM quantum computer. So it's called air simulator. And what you can do is import this and print basic air different simulators. What simulators out there? There's a QASM, quantum something simulator. There's a static vector simulator, similar, and there's a unitary simulator. None of them, I think, includes the real thing. But as you can see, if you can call a simulator, you can call the real thing as well. So first, we import that. The next thing that we do is we import all these simulators, and we import a new thing called transpile. Transpile is not compile, but it compiles quantum circuit into something that runs. In other words, it establishes those connections between qubits. Now, qubits, they can be photons, then can be ions, but we're not going there yet, right? Instead, here we are creating a small quantum circuit. When you create a quantum circuit with qubits, 2 qubits, that really gives you 2 qubits, but they are also with 2 regular bits because you want to measure what the result of a qubit calculation was, but you don't have to mention it here. Okay, now what we're doing here is we're putting it into some special state. What does it mean, putting it into some special state? That means that bits, they are either 0 or 1, but qubits, they can be 0 or 1 or anything in between until you measure them. So when you measure them, then they are they are also 0 or 1, but with a probability, and that's where the power of quantum computing comes in. So first of all, put it into Adamar state, put it into, as we call, superposition state. It's not 0, not 1, something in between, and apply this to a to the bit 0, to the very first one. And then what you do is negate it. Take the bit 0 and forgot what this other parameter is. Does anybody remember? Well, that is something I need to remember next time. In any case, you put it into a negator, so it was 0 becomes 1, 1, 0, and then you measure all. And then you can take a simulator and actually run that circuit. What you get is 0 with probability of 0.49 and 1 with the probability 0.51. And if you run it a few more times, it will probably give you another number. That is, I think, a very interesting exercise, and I'm suggesting we run it. Now, there are 2 ways to run it. Run locally here or run on Colab. And since I want to give something that is available to all of you, what you do is the first thing, follow me, and I watch the chat, and you download that. Okay, you download that, and it goes into your download folder right here. That was downloaded in lab. Okay, but of course you cannot run it. We will put it into Colab. So go with me to Colab. That will be the link. That's where we're going. So I'm giving you this link, and I'm putting it in 2 places. First, I'm putting it, run it here. There you are. Run it in this environment. And secondly, I'm really running it in this environment by uploading it there. Okay. Open, no, not open notebook, but upload notebook. Upload notebook. Choose the file. It is in my downloads, so right here, boom, and amazing, right? You give it to the Colab, and you see it in Colab. Now, that's just an explanation. That's what the Python notebooks do for you. They say that is just an explanation, and what you can do is run that. Oh, instead of running, I opened it. So if you hit enter, you can see what it is, but if you do shift enter, it becomes normal. Then that's an explanation of all those simulators, but right now we're much more interested in running that. So we'll skip all the explanations because that's not a runnable cell. It's not code. Code starts here. So we come here, and of course, we should error out. We remember that when it says from Qiskit and there is no Qiskit, you might set up it locally. But if you're running in Colab, it should give you an error. like this. What you do is before it uses this Qiskit, you are importing this, installing it. You're saying exclamation point, which takes you out of this pip install Qiskit. So it installs it. Now that is a cowboy kind of combination when you change the lab as you go. So in class, I would be nervous to do such things, but we're all friends here, so we can accept a little risk. It might not import correctly. Usually it does. And so every time that something doesn't work like this, you can just correct it right here in Colab. But there is a good side for that. When we're doing this, you're more comfortable. You know that you can deal with little errors, not a big deal. So it imported this, then it said, let me run it, let me import it. And then it said, you asked me to print it. So here you are, right here. So print the basic backends. And here are the 3 basic backends. My next step is I already imported Qiskit, so it should run, and I am bringing in more classes. Quantum circuit, that's the basic thing we will need it for anything that we do. We need quantum circuit. And then we need the basic AER. We know it's there. It's the simulator thing, but we don't have the class to deal with it. So now we do, and also transpile, that's kind of uh, convert the code into something runnable. So let's do this. That should work. We imported these classes. We're creating a quantum circuit. And now we are actually creating it in a superposition state. We're making it not 0 or 1, but anything in between. We're negating, we're doing the CX. This collab is amazing. It gives you the documentation, right? How does it do that? Oh, probably picks it from the library. Okay, let's say I have some chat. You get this, oh, beautiful, Aisha. You get these results and they're not what I showed you, right? That's what you get, 497, 503. Now the total is 1,000. That is okay. But then you run it again and you get 478 and 522. Again, the total is 1,000. That's beautiful, but you get different results. That's because we're doing real stuff. We're doing emulator, but emulator tries to be as much a real quantum computer as it can. What will I get? That also tells me, Aisha, that you're actually running. Otherwise, you wouldn't get this. Okay, so then I'm creating, choosing which backend I want. I want this. Then transpiling, so that becomes a real executable. It's just like exe. You can think of it this way. And run. Well, after you run, the results are there, but you haven't looked at them. So here you are looking at them. Let's do it. I get 505, 495. Really, I have put it into superposition of half and half. So it should be around 500 these results and 500 these, but of course it will change every time. For example, if I go back again, run this and then run that, then I get different numbers, 504. I think that's awesome, and you were able to do it. If you have any problem, just tell me. And then I have some exercises for you for your pleasure and fun. And that is exercise 1. Do the same code, copy paste that same code, but instead of QASM simulator, use state vector simulator. You can research what the difference is, but we're only interested in mechanical movements. What you need to do to use a different simulator. Well, I can do this. I can say, don't copy everything, just change the simulator and see if that works. And what difference does it make? right? So we're doing this and we're getting some results, and it's interesting. It gets 0, 0, and 1, which I don't even understand, but that would be the simulator. Now, another exercise that I'm suggesting here is that you do the same, but you use a different package. Well, let's try that. Let's try that. We said import a different package. We put it into import right here, right? And it's not basic air, but air. I can import both, no problem. But then when I'm using it, so again, the same thing, but here instead of basic air, I will just say air. Okay, let's try to get that. And it says there is no such thing. It says you need this. Well, how about we do install it? Okay, right. We go back to the place where we were installing in the beginning, and we don't want to install it again. Instead, we will create another cell, okay, and we will install it here and try to run it. Except that, of course, I need to say exclamation point pip install. So let's see how that installs. Now, if you do all of that, then you feel much more comfortable, more and more comfortable, as Alice in Wonderland would say, comfortable and comfortable. Okay, now this is what didn't work. Well, just in case, let's not skip. We got that, but that requires a different simulator, and it worked out of the real thing. So probably it will work here too. And that's interesting. I got some new numbers. So that was my second exercise. Use a different picture. Now, and the last thing in this lab that you can run these operations to monitor what's going on. So of course, all the jobs are done by now. They're not running, but let us do this. Let's run this, and yeah, it's done because it's very short job. Now, what was the job ID? Well, yeah, they had certain ID. Is it running? Yes, it's not. It should be done. But the results, you can look at them again and again. Numbers change. And then you can even take this result and convert them to a complete printout of everything. So you see backend. That reminds me a lot of when you were running IBM jobs on the mainframe with the status. All right, same people after all. I think that is a good exercise. We're done with that. I will stop share. And I also see somebody else came. No, just 3. All right. And what we have done is looked at the latest news, and we found out about this muon, that it opens, that it is fatter than electron by 200 times, that something doesn't jibe with the way they measure it. And they said, guys, your theory is wrong because it has not 2 for the spin, but 2,0,0,0,2. And that's not an error of measurement, but that's a super important. So what they did is they took that experiment and they sent the ball to their court, to the theoretician's court. And the guys in theory should now explain it or drop their theory and suggest there is a fifth power that they never thought about. And that's all because this measurement. All right. That's what we did. We saw this. If you want it, then it's all here. It's on August 11. These are all the links you want to review. They're here. We looked at what Intel is doing, and now, at least if you're a university, you can buy quantum computer for yourself. And we also did an exercise or lab. So at the risk of torturing you, I'll show you more labs this week and probably next week because I'm running them myself. I need to get ready for the test. All right, questions? Was there anything that wasn't really clear when I explained this to you? Should I concentrate on some other? And if you don't want to tell it to me here, well, you can always email. You can say, Mark, next time explain this better or do this more or less. And that's my email. Okay, so you can write directly. And I wish you all guys a great weekend and then a great week. Okay, thank you very much, Kenneth. And a good year coming up. All right, so saying goodbye for now and see you next time. Thank you.